Hello friends, I am myself Pavan Binu Matthew and today I am going to discuss about the topic Stark effect. So what is Stark effect? Stark effect is actually the phenomena of splitting or shifting of the spectral lines of atoms or molecules in the presence of external electric field. It was discovered by Johannes Stark in 1913 while he was studying about the hydrogen spectrum. There is a historical context. Johannes Stark won the Nobel Prize in Physics in 1919 for this discovery. Stark effect is a key phenomenon in quantum mechanics and spectroscopy where it allows for the study of electric field at the atomic scale. This effect has provided insights into the internal structure of atoms and their interaction with external fields. So let's go into electric fields and atoms. Atoms typically have discrete, well-defined energy levels when they are not disturbed. When an electric field is applied, in case of Stark effect, it interacts with the atom's electric cloud, causing a distortion or perturbation of these energy levels. As a result, spectral lines split, which can be observed through spectroscopy. Now let's go into the quantum mechanical background. As we know, atoms have quantized energy levels determined by the quantum numbers, the principal quantum number n, azimuthal quantum number L, and the magnetic quantum number m. In an undisturbed atom where there is no external field, these energy levels are stable. The introduction of an electric field perturbs the Hamiltonian of the system, leading to new energy levels. The perturbation theory in quantum mechanics is used to calculate these changes, explaining how small external influences affect the system's energy. The quantum mechanics, the famous equation of Schrödinger also explains this interaction. Now let's go into the types of Stark effect. There are two types of Stark effect, the linear Stark effect and the quadratic Stark effect. Linear Stark effect occurs in systems where degenerate energy levels are split by an electric field. The energy shift is proportional to the strength of the electric field, while quadratic Stark effect occurs in non-degenerate system where the energy shift is proportional to the square of the electric field. This is more commonly in atoms or molecules without degenerate energy levels. Linear Stark effect is often seen in hydrogen-like atoms, while quadratic Stark effect is often seen in helium or more complex atoms. Now let's go into the linear Stark effect in hydrogen. In a hydrogen atom, the first order Stark effect splits the degenerate energy levels in response to an electric field. The electric energy levels with different magnetic quantum number ml are split by the electric field, and the energy shift is proportional to the field and strength E, and it is calculated by delta E is equal to EZ, where Z is the electron's position along the electric field direction. Now into quadratic Stark effect. For atoms without degenerate energy levels, the second order Stark effect is dominant. In this case, the energy shifts quadratically with the electric field. Delta E is equal to E square, proportional to E square, and delta E is equal to alpha E square, where alpha is the polarizability of the atom. The quadratic Stark effect generally causes smaller energy shifts than the linear Stark effect. Now let's go into the energy splitting during the Stark effect. This graph shown here shows the splitting of energy levels in a hydrogen atom using under an electric field. The energy levels splits based on different quantum states, and the degree of splitting increases with the strength of the electric field. The amount of splitting depends on the magnitude of electric field and the of specific energy level configuration of the atom. Now let's go to the experimental observation. The spectrometer setups are used to measure the splitting of spectral lines due to the Stark effect. The experiment involves placing atoms in an external field and observing the resulting shifts in spectral lines. The Stark effect is important in both laboratory and astrophysical applications where electric fields can be studied in detail. And in real world uses such as electric field mapping in laboratory plasmas or stellar atmospheres where the Stark effect provides clues about the electric fields in stars. Now let's go into the applications of Stark effect. It is usually used in spectrometer or spectroscopy used to study atomic and molecular energy levels. They are used in stellar atmospheres where Stark effect helps in studying electric fields in stars. It is used in quantum optics where this effect is relevant in the design of quantum systems and technologies, and it is also used in laser physics where Stark shifts influence laser frequency stabilization. Now let's go into some of the differences between Zeeman effect and Stark effect. Where Zeeman effect describes the splitting of spectral lines of an atom in the presence of strong magnetic field, Stark effect is the splitting of spectral lines observed when the radiating atoms, ions or molecules are subjected to a strong electric field. Zeeman effect can be observed in an applied magnetic field, and it is due to the result of interaction between magnetic moment of the atom and external magnetic field, while Stark effect can be observed in an applied electric field and arises due to the interaction between the electric moment of the atom and the external electric field. So what are the modern applications in the technology or due to Stark effect? It is used in quantum computing. Stark effect is used in qubits for error correction and coherence control. They are used in semiconductors where the effect influences the behavior of electrons in semiconductor materials, which is crucial for electronic devices. They are used in lasers where Stark effect helps in stabilizing and tuning laser frequencies. They are used in molecular Stark effect, important in molecular spectroscopy and microwave technology. Now what are the summary of the key points that we discussed here? Stark effect demonstrates interaction between electric field and atomic energy levels. It has applications in spectroscopy, quantum mechanics and technology. The effect remains a crucial topic in modern physics with future research aimed at leveraging it in fields like quantum computing and semiconductors. Thank you.